All right, so next up is how do you visit all nodes in order? How do you print all nodes in order? So how would I print 1, 3, 4, 6, 7, 8, 10, 13, 14? How do I print all these nodes in key order? Well, this is called a traversal, and this is going to be an in-order traversal. So the way you print things in order, or visit nodes in order, is you recursively look to the left until you can't look to the left anymore. That's out of order. Which is ironic. You go to the left, and then you print out the node when you can't go to the left anymore, and then you recursively go to the right. So for example, if I want to print all these nodes in order, and I start at the 8, I go left. I'm at the 3, I go left. At the 1, I cannot go left, so I print the node out. So I'll get a 1. And then I visit to the right. There's nothing to the right, so then I return. I'm at the 3. I've already visited the left, so now I'm at the 3. I print the node, again, this middle operation, and then I go to the right, left, print the 4, return, print the 6, go right, no left or right, print the 7, return, 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 print the 8, and so on. What is the running time of this? Again, so since we're visiting all nodes, it's going to be linear. It might seem like we're doing a lot of extra work, but really we're just sort of traversing down the tree and then back up the tree. So for each node, we're essentially doing a constant amount of work of traveling against its pointers to its children and pointers back up to the parent. So that's called an in-order traversal. There's also a post-order traversal. Not sure why that animates that way. There's also a post-order traversal in which you would visit the nodes last. So, for example, you'd go left, can't go left, can't go right, and then do something with the node. So one example of doing a post-order traversal is if you're trying to evaluate an abstract syntax tree. So this thing here above is essentially an abstract syntax tree for an arithmetic expression. So you would go left, can't go left, can't go right. You would return the 1 to the plus operation. And then from the plus, since it's a post-order traversal, you have to do its right recursive call first. So you go right, go left, return a 4, go right, return the 7. And now that I've got, this is the first node, the subtraction node here, is the first time when I've evaluated both the left node and the right node. So I'm going to evaluate the current node, visit the current node. So I would take 4 minus 7, which is -3, and I'm going to return the -3 up. And now I've done both sides of this one, so I've got 1 plus -3, which is going to give me -2, and I'll return the -2 up. And then I do the same thing down the right-hand side. So post-order traversal is used a lot in developing programming languages, for example. Finally, there's something called a pre-order traversal, where I do something with the current node, and then I visit the children. Do something with this node, visit its child, do something with this node, nothing to the left, nothing to the right, go back up, then go to the right. So basically doing your operation on the node first before visiting the two children. So here is an example of another application of doing a tree traversal. So I'm not sure if you're aware of this, but the DOM, the document object model, that's how you represent HTML code. That's how the browser represents HTML code. So let's say that we wanted to do some sort of operations on everything that shows up on the screen of a website. So that would be everything inside the body of an HTML document. Here's some code. It starts down here. I'm going to call walk the DOM, and I'm going to pass in as the node the body of it. So that means I'm going to pass in the body node here. And what does it do? It just prints something out. And by that I mean this walk the DOM function is this function here. Sorry, I'm just my JavaScript syntax here was weird. I was thrown off because I've got walk here and walk the DOM here, and I just didn't do a great job of writing JavaScript. I should really have just, deleted all this and called this the walk function, but here we are. So that'll be something I'll fix later on. So in my walk function, I give it a node, and I give it a function that I want to apply to the node. So what kind of traversal is this walk the DOM function? Is it a pre-order, in-order, or post-order traversal? Well, the thing I'm doing with each node is this function call here. So this is the function I'm passing in down here, which is just printing off the current node at some sort of indentation level. So I'm doing something with the node before I visit the remaining nodes. So the DOM isn't necessarily a binary tree, so it can have the body and it can have multiple children instead of just a single child. But this is still going to be a pre-order traversal. And why is that? It's because I do something with the current node before recursively searching on the child nodes. So what kind of traversal is this? It's a pre-order traversal. What is the output? So for anybody who's not familiar with HTML, this might be a little tricky. But essentially, if I pass in the body node, the first thing I do is call the function on it, which means I'm just going to print off the node name. So I'm going to get body, and then I increment the indentation level, and then I look at the children of the body, which would be the header, the main node, and just those two nodes. So I'll print off header. Header doesn't have any children, so then I print off main, and then I recursively print off its children, which include the h1 tag, the ul tag, and the li tag. So this is a pre-order traversal over the DOM, and this is something you do pretty commonly when you develop something like a web app. All right, so we've talked about insertions, insertions. How about deleting a node from a tree? Deletion is often the most difficult task because it requires sort of repairing the tree as opposed to just adding something at a leaf node. When you insert, you can always get away with just adding something as a leaf node. You don't always get so lucky with that easy case for deleting. So the first thing you do when you're deleting is you just have to search for the key. And the easiest case is if the node that you found has no children, you just delete it. So we can easily delete the 1, the 4, the 7, and the 13. Case 2 is when the node has just a single child. So for example, the 14 is pretty easy to delete, the 10 is pretty easy to delete, and I think those are the only two nodes with just a single child. So how do you delete them? You just splice it out. So I just remove this one and move the 13 up into its space. Case 3 is a bit more complicated. If the node has both children, so how do I delete the 6, the 3, or the 8, for example? How do I delete those nodes? Well, I can find the node's predecessor, and then swap the node with the predecessor, and then delete the node. So, for example, what's the predecessor of 6? We know that the predecessor is going to be the minimum of the left subtree, so that's going to be the 4. So I can just swap the 4 into that place, and then delete the 6. So why am I guaranteed that the 4 is not going to have any children? Well, we just said, how do you find the predecessor? It's the maximum of the left subtree, and a maximum element is at most going to have one child. So it's pretty easy to splice in. All right, so for the next video, I'd like you to work on this problem. How do you compute the ith order statistic using a binary search tree? So again, the ith order statistic is the sort of ith biggest number, or smallest actually. The ith smallest number. So the first order statistic is the 1, the second order statistic is the 2, the third order statistic is the 3. How do I find those? And in the next video, we'll come back and solve that one together.